and good afternoon. And I am really thankful to Andrea for the invitation. It's a privilege for me to be here and to give this presentation on Chromonic liquid hedgehogs. Chromonic liquid crystals are a relatively new class of lyotropic liquid crystals with applications to both industry and living systems. They are a crossroads between elasticity and geometry of the submatter. And I will start with an introduction to pneumatic liquid crystals in order to fix the lexicon. And then I will describe the energetic of Chromonic liquid crystals, starting from the classical Frank theory, its paradoxical consequences when this theory is applied to Chromonic liquid crystal droplets immersed in an isotopic phase, and then our new theory. And then the talk will find a means to differentiate the classical theory and our proposition. And liquid crystals are mesophases, which are intermediate state of matter, which may flow like liquid, but have also properties typical of a solid. Indeed, the existence of these mesophases is due to a particular arrangement of the orientation of the elementary sequence, which can be single molecules or assemblies of these molecules, when they pass from a ordered crystalline arrangement, which is typical of a solid, to a disordered phase, which is typical of a liquid. And systems in which the liquid crystalline phase is induced by reducing the temperature from the isotropic liquid phase are called thermotropic liquid crystals, and they are found in, for example, in man-made displays, and their elementary constituents are single molecules. And there are another class of liquid crystals, which is called lyotropic liquid crystals, where the elementary constituents are molecular assemblies in a solvent, and the concentration is the driving parameter for the order. And they are found in solvent or living systems. And the elementary constituents of the phase, which are rod-like molecules of the typical dimension of 5 Armstrong by 20 Armstrong, or assemblies of molecules, possess orientational ordering, but not positional ordering of their center of mass. And their local average orientation is represented at the macroscopic level with the unit vector, which is called director. And the director is a unit vector, and symmetry, which means that if we exchange the head and the tail of every elementary constituent, their interactions with the neighboring molecules remains unaffected. And so the kinematic director is non-polar. And the theory which describes the pneumatic liquid crystals must be indifferent to changes n in -10. And the spatial distortion of the director is measured by its gradient, and it may become singular where the director actually defects. And here there are two defects which are concentrated in isolated points. And the ground state or natural state, which is the director configurations into which the liquid crystals relaxes when neither external actions nor anchoring conditions affect their orientation. For pneumatics, the director in this ground state is obtained when the director is a uniform in space, and so it is constant, no distortion has to be seen at all, and each gradient vanishes. And Chromonic liquid crystals are a peculiar class of lyotropic liquid crystals, which are non-chiral, and drugs, DNA, and oligomers are the most common examples. Their molecules are plum-shaped with an aromatic core and polar groups on their peripheries, and have a typical diameter of 1 to 2 nanometers and a thickness of 0.34 nanometers. And these molecules tend to stack face to face in order to form columns of typical height 10 to 100 nanometers. And these columns can order in the nematic phase, which is described by the director field N. And so far, the elasticity of Chromonic described by the classical Frank theory, but a contentious point is whether or not the elasticity of Chromonic liquid crystals is well described by this theory. And the classical theory for this bulk free energy, also called elastic free energy, as given by this function, where B is the region occupied by the liquid crystal, and W is the elastic free energy density, which must obey a list of requirements which describe the properties of the materials we intend to model. And in particular, it must be frame indifferent, which means that it must be the same in two frames. It must be even in the director in order to account for the head-tail symmetries, and so it must be indifferent changing of n into -10, and it must be positive definite, and this property deals with the fact that the elastic free energy measures the cost associated with producing a distortion in natural state, to which zero free energy is associated. And the most general frame different function W, which is even in n and quadratic in the gradient of n, was put forward by Frank in 1958, and there K11, K22, K23, and K24 are elastic constants, which are referred to as splay, single twist, band, and saddle-splay. And this is because they are associated to the orientation field, where distortion energy is proportional to only one of the terms in this formula. And for display mode, we see the tendency of the director to splay, to extend like a fan. For the twist mode, to wing, to twist, and for the bend, to flex. And for the saddle-splay term, we can only provide a director field with distortion energy is only approximately proportional to this term, and it is a null Lagrangian since its integration of over the bulk reduces to a surface energy. And here is a differential model decomposition of the Frank free energy, which is proposed by Selinger. And here the distortion modes are splay, the twist, which is also called double twist, bend, and octubular splay. And I want to focus the attention for the following part of the seminar on the director field, where distortion energy is proportional to the term involving the twist elastic constants and the saddle-splay elastic constants. This orientation field is the double twist, and has only seen 0 among all modes. And here it is depicted pictorially, and we call it double because for every radial direction we see that the director rotates in opposite direction, as it is vertical in the middle. Yeah.
This formula here is equivalent to the previous formula.
Yeah, it is equivalent to the previous one, and there are two different interpretations of the twist, which is multiplied by the constant K22, and the distortion multiplied by K22 minus K24. And I present this formula because I'm interested on these differences of elastic constant, and it is useful for the following. And yeah.
Well, the question is, this is an expansion.
No. The formula is the same, but the K24 term is
the previous formula.
this one.
It's quadratic, yeah. So it's the most general quadratic expansion.
Yeah.
And then can there be like non-linear terms for the
Yeah. We prefer this for the form is this because it's the most simple.
Yeah.
And we can add the other terms, but
physically does that happen? Are there phenomena that can only be explained by expanding further?
I will present a theory which will expand this theory, and this is the most general, which is quadratic. And then I will present that this formula, in my opinion, is not adapted to describe chromonic liquid crystals, and then I will add more terms. Yeah, thank you for the question. And okay, and the Ericksen's inequality ensure that the Frank free energy is a positive definite and vanishes on a natural state for which the gradient is 0. And so the Frank theory for pneumatics is based on the assumption that in the ground state, the pneumatic director has everywhere the same orientation. And so every distortion from the natural state, from the constant state, costs energy, which is positive. And we turn our attention on this inequality involving the K2 elastic constant and the K2 elastic constant. And chromatic liquid crystals in 3 dimensions have become of interest because when they are confined in a cylindrical tube, which is subject to the generic planar boundary conditions, which means that the director must be tangent to the boundary, but free to orient in any direction. The director field does not acquire the spontaneous natural state in which it is constant along the axis, which is the only uniform orientation which is compatible with the boundary condition, but it acquires instead a twisted orientation which is escaped along the axis, which means that the director rotates clockwise or counterclockwise with equal probability since the lack of chirality of the molecular aggregates, and swinging away from the axis on the lateral boundary. And despite this lack of uniformity in the ground state, the classical Frank theory has been applied to rationalize this experiment with capillary tubes. That's the problem. And here is the conundrum. We adopt the Frank theory to describe the elastic properties of chromatic liquid crystals in order to accommodate the experimental finding and to justify the twisted ground state observed in clinical capillaries. The elastic constant K2 must be small, very, very small, so small that is less than the K2 elastic constants in order to violate the Ericksen's, one of the Ericksen's inequality, which has been proposed in order to ensure that the free energy is bounded below. And this makes sense because we have that with the positive definite free energy density, the minimum state is obtained when the director is constant. And so we can, with the boundary condition, we can provide a constant director, but it is not with the orientation with the lowest energy, and so we have to violate one of the inequality, and the inequality which is violated is that. And so in rigidly confined systems, the generate boundary conditions save the day and the ground state. Indeed, this is provided by the form of the K2 integral in the Frank energy, which has this form when the general planar boundary conditions hold, and it ensures that the Frank free energy stored in a cylinder is bounded below, and it is also well behaved despite the violation of the Ericksen inequality. And the lack of pathology emerging from the lack of boundedness in the general setting, we study the local stability of the escape twist fields in a cylinder, and we find that they are locally stable. But this latent pathology emerging from the application of the Frank theory to the elasticity of common liquid crystals reveals when we study pre-boundary problems. And so when we study a chromonic liquid crystal droplet, which is immersed in an isotropic phase and can adjust its shape to the surrounding, and in this case, the Frank theory predicts that these droplets would disintegrate into an myriad of smaller tactoids, while the total energy plummets to minus infinity. And to be more precise, so I only say that in this problem that we have that our droplet can adjust its shape to the surrounding, and the shape of the droplets becomes an unknown of the problem, besides the director field within it. And we have that is a perimetric constraint which prescribes the volume and associated a fixed volume to the shape, which is not prescribed, arises. And we must supplement the bulk free energy with the surface free energy, which is concentrated on the boundary. And as an example of the minimizing sequences which drives the total energy to minus infinity, we prove that when a chromonic liquid crystal droplet submerged by an isotropic phase is confined between two parallel plates 2L apart, it would split an step into halves, driving the total energy to minus infinity. And we also prove that a generic chromonic liquid crystal droplet can be split into unequal components in a way to reduce the total energy, and this prove the instability, the instability of every droplet against the domain splitting. And so this prediction of the Frank theory are in sharp contrast with a wealth of experimental observation of chromonic liquid crystal tactoids, which are stable in the deposit region. And so we need that the Ericksen's inequality is not violated in order to justify the very existence of the observed twist tactoids. But on one hand, to justify the twisted ground state, we need to violate one of the Ericksen's inequality. But on the other hand, this must be verified. And so to overcome this contradiction, we propose a minimalistic free energy, which adds to the classical Frank free energy density, a quartic term in the double twist mode, and hence the name quartic twist theory. And the quartic twist energy density is, unlike the Frank free energy density, is bounded below when the Ericksen's inequality involving K22 and K24 is violated, and it is minimum at the intrinsic degenerate double twist with the two equivalent spiral variance, which is represented by these distortion modes, and only P is non-zero. We see that A, which is the characteristic length which is introduced by the model, can encodes the bare length scale associated with the double twist, which is favored as ground state. And for the physical sides of this length scale, it may fall in a very wide range. At the lower end, we can place the persistent length of the molecular order, and which characterizes the flexibility of the aggregates, and so it can be the similar to the height of a column, and so 10-100 nanometers. But the upper end is hard to make definite, and So we shall treat A as a phenomenological parameter to be determined experimentally. And as a consequence of the ground state envisioned by this theory, the total energy obeys a uniform lower bound, where 0 is the volume which is fixed. And this lower bound prevents the existence of the minimizing sequences which with driving energy which generate the paradoxes within the concrete energy. And then we want to mark a difference between the classical theory and the quantitative theory on the basis of the different structure they predict for the core of hedgehogs, which are the most common nematic defects in liquid crystal sciences. They are point defect with a topological charge +1. And we are interested in both qualitative and quantitative differences. And we shall describe the orientation of a trial director field within a ball of radius R and center at x,0, enforcing homeotropic boundary conditions, where nu is the unit normal to the boundary. And this field can be potentially rich-in-twist as it would seem fit for a material with a small KH2 elastic constant, such as that of the Chromonic crystals. And the point defect that we want to study place themselves between the radial hedgehog and the hyperbolic hedgehog. And here I present the field lines of the radial hedgehog on the left and on the hyperbolic hedgehog on the right. And they are the integral lines to which the director is tangent. And they are drawn in black on the equatorial plane of the droplet and in red on the median plane. And the whole picture is obtained by rotating these lines around the polar axis. And the radial hedgehog is described by the director field, which has a point defect at the center of the ball. And the hyperbolic hedgehog is formally obtained by applying a rotation to the radial hedgehog by angle pi about the unit vector, which is the symmetry axis. And our twisted hedgehog wants to interpolate in space between the radial hedgehog and the hyperbolic hedgehog. And here is general appearance inside a sphere enforcing homeotropic boundary conditions. And we can see an inversion ring of radius that we call our star, which is on the equatorial plane, and it is here depicted in blue. And it is called inversion ring because it separates the two opposite spiraling regimes. And here the integral lines seems to coalesce in the ring, which looks like a destination, but it is instead regular since there's no discontinuity of the director field. And the dimension of this ring is obtained by the energy minimizing twisted hedgehogs, and we shall do so for both our theory and the classical theory.
Sorry, what's the meaning of that? What's the meaning of that?
Okay, the R is this line are the lines to which the director is tangent.
Distribution
And so, sorry.
The distribution of the director. Distribution of the director.
Yeah, and this is the direction when it is plus n, and so the director, we see that it starts to go away from the ring, and then go inside the ring, inside of the inversion ring, and so there is the we see that there is an inversion of the side of the ring. If the arrows are exchanged, we have the direction of the minus sign. They are equivalent in the theory. I only put this arrow to show this different behavior. and but n and minus n are actually the same in this theory. Thank you for the question. And okay, and here is the formal definition of our twisted hedgehog. In a spherical frame, the trial twisted hedgehog is obtained by acting on the radial hedgehog through a rotation of the now variable angle alpha, which depends on the radial coordinates, about a fixed axis. And when alpha is equal to 0, the twisted hedgehog reduces to the radial hedgehog, and when alpha is equal to pi plus minus pi, reduces to the hyperbolic hedgehog. And then we have to impose and retract boundary conditions, and so this condition must be satisfied, and so on the boundary we have that the director must coincide with the radial hedgehog. And we identify the inversion, the radius of the inversion ring that we have called our star as the radius at which alpha is equal to pi over 2, and so it is tangent to this circle around the center of radius r star on the equatorial plane, which is the inversion ring that we have called it. And we interpret this twisted hedgehog as the director orientations which replace the radial hedgehog when it becomes unstable. And the radial hedgehog is the universal solution, since it solves the equilibrium equations of every functional with free energy density is frame indifferent. And here I depicted the region of the of interest of the local stabilities of the radial hedgehog, and they are fine to coincide within both the theory. And in here, K1 and K3 are defined as the ratio between K11 and K22 and K23 and K22 respectively. And in the pink region, the radial hedgehog is the local minimizer, while in the blue of the free energy, both in the quadratic and in the quadratic case, and in the blue region, it is no more a minimizer, but there is a continuum of minimizers, all with the same energy. And so our twisted hedgehog, which is parameterized by this angle alpha and E, we find the symmetry axis fixed, and letting the symmetry axis fixed with these optimal angles, we will enclose this continuum of minimizers. And yeah.
Maybe I just missed it on your previous slide. Is the angle alpha uniquely?
No, it is arbitrary. It is
This will be a solution for any choice of the angle alpha.
Sorry. This is a function which depends only on the radial coordinates, and we don't know anything about this alpha, and we only know that it must obey homeotropic boundary conditions. So we kept this E fixed, but it doesn't intervene in the elastic free energy because E is in this case arbitrary. And we have that we minimize through we pass it through problem dynamic systems, but I don't show you that, but in this representation, but if you are interested, I will show you. And but we find the minimizing angle alpha, which minimizes the free energy, and then we let E vary, and so we find all the continuum of minimizer which has which have the same energy, but they differentiate because they are oriented in different ways. Thank you for the question. And the Chromonic sunsets yellow in water at a concentration of 30% at the room temperature the bulk elastic constant of this Chromonic sunset yellow was found by Zhu et al. And the ratio is delivered as K11 over K22 is 6.1 and K33 over K22 is 8.7. And these red dots mark the data for the SSY solution, and we see that they fall in the region of instability of the radial hedgehog. And since the seminal work of Laventovic and Terentev, we know that the radial hedgehog becomes unstable as a result, it becomes twisted as a result of cooling of the pneumatic to a temperature nearing the pneumatic kinetic A transition. And here a defect 4 is identified and it is delimited by the inversion ring, where the spirals invert the winding sense. And the droplets which are observed have a radius of about 30 micrometers, and the radius of the internal ring is a fifth of that. And the classical theory describes well the situation for ordinary with ordinary pneumatics, but as we will see in the following, it seems to not well characterize the defect 4 that chromonics generate when they are confined into spherical cavities, enforcing homeotropic boundary conditions. And examples of and these are produced into a polymeric matrix. And examples of these spherical cavities are in this figure, and they are produced for us by Ciucchi De Santo and Spina. And they include a sunset yellow solution in water with a concentration of 30% in temperature at room temperature. And as we can expect it from the smallness of the twist elastic constants and from the fact that the data for the SFY in these physical conditions fall in the region of instability of the radial hedgehog, we see the appearance of the inversion ring. And we see that unlike the classical pneumatics, the core enclosed by the ring occupies 1/2 or more than 1/2 of the spherical cavities. And it seems to be more detailed than structure. And theoretically, the radius of the inversion rings depends on the radius between the characteristic length A introduced by the model and the radius of the spherical cavity. And so we can provide an estimate of the value of the characteristic length that I've said before we treat as an experimental length, that make numerological length to be determined experimentally. And we provide an estimation of A through a direct study with direct observations of the radii of the inversion rings compared to those of the corresponding spherical cavities are. And I can give the detail of how we provided these estimates at the end of the presentation, but I want to say that we provide 3 estimates for A, differentiating the case in which the samples are newly done after 1 day, and observed after 1 day their generation, and observed after 2 days. And in the following, for the comparison between our theory and experimental observations, I prefer to focus only for simplicity to samples to spherical cavities which belong to samples which are observed after 1 day their creation, for which we consider the estimation of A, which we have done, which is 41.1 micrometers. And we consider in the spherical cavities which is represented in this figure. and which has a radius of 43.5 micrometers. And this droplet is luckily recorded at the moment when it is oriented in a convenient way to the analysis of the structure as a whole. Indeed, it is viewed along the symmetry axis, and so the core is evident. And since it belongs to a sample observed after 1 day, we consider it as 41.1. And then I will present the outcomes of both the theory for the energy minimizing twisted hedgehog. And I recall that the Frank theory is successful for ordinary nematics, such as those observed from in the work of Untitled Chapter. And we introduced this dimensionless parameter, which is given by the ratio between the characteristic length and the radius of the spherical cavity. And we find the energy minimizing twist angles alpha in the Frank theory when lambda is equal to 0 because A is 0. And in the twist quartic theory, since lambda is greater than 0. And a first qualitative features differences between the two theories that we can find is that is the asymptotic value of the twisted angles at the center of the sphere, which is pi only within the twist quartic theory. And so the radial hedgehog and the twisted hedgehog at the center of the sphere are completely bridged only within the twist quartic theory. And moreover, the dimension of the inversion ring compared to the radius of the cavity is estimated to be much different in the two theories. And for definiteness, I present the case of the spherical cavities, which has, as I said, a radius of 43.5 micrometers. The value of A is those estimated for the samples, and lambda is 0.94. And for sunset yellow, in the physical conditions of the experiment, the ratio of the elastic constant is that. And we plot the two minimizing twist angles in the quartic theory in red and in the quadratic theory in blue. And the dashed line intercept at the pi over 2 intercepts the graph at two values of rho, which is a scaled coordinate, which is given by the ratio between the radial coordinate and the radius of the sphere. And we see that this value of rho, which I call rho star 0 for the classical theory and rho star lambda for our theory, are appreciably different, and they represent the scaled inversion rings predicted by the two theories. To better understand this result, I'm interested on the equatorial field lines, and so the field lines on the equatorial plane of the spherical cavity. And we see that, as I said before, that the defect core predicted by the two theory are different, very different, qualitatively different, and quantitatively. Yeah.
You might have missed this, but the quadratic theory is the initial Frank theory.
Yeah.
And how are they getting the twisted defect core in the Frank theory?
For the smallness of the K22 elastic constant, because we have an anomalously boundary conditions, and so the radial hedgehog is always a solution. But in the region I presented before, we are with the elastic constant of the sunset yellow in the region of instability of the radial hedgehog, and so we expect a twisted configuration inside the sphere, both for the classical theory and for our theory, and this is given by the smallness of this constant. This is constant.
Is K2 less than K2 in the quadratic theory?
In the quadratic theory and also in our theory.
The K2 theory you compensate by a higher order term.
Exactly.
In their theory, it's actually good close.
Yes, but we have homeotropic boundary conditions which are fixed, and so we can not consider this term because it is a
Situation boundary condition.
exactly, and so we don't have problems with the divergence. If the droplets could split, we could have this problem because splitting the droplets would drive the free energy to minus infinity. But here are in a polymeric matrix, and so they are fixed and they cannot split thanks to this polymeric matrix. I've talked with the experimentalist, and they cannot produce, for example, a spherical cavities without this polymeric matrix and homeotropic boundary condition which contains sunset yellow. And so, but we can to answer your question, sorry, we can only study these cases because the shape the shape is fixed and the homeotropic boundary conditions are fixed, and there is no soft sampling. Thank you for the question. And as I said before, the defect 4 is predicted by the quadratic theory to be much larger than those predicted within the classical theory. And according to the asymptotic value of the angles at the center of the sphere, we have that within the quadratic theory, we have that the director describes the Archimedean spheres instead of the logarithmic ones. And then I return to the droplets under consideration, and I draw the appearance of the structure predicted by the quadratic theory, and I was very, very happy. And we can see that our theory predicts an inversion ring, which is an order of magnitude greater than that produced in the classical theory, in absolute term 23 micrometers against 1 micrometer. And we see that our theory seems to capture the internal structure of this droplet. And here is another spherical cavities which has the same structure of the previous one, but it is rotated relative to the observer. And so we draw the integral lines which the general appearance of the structure predicted by our theory, but when the droplet is viewed at an angle with the symmetry axis. And also in this case, I think that the internal structure is well characterized. And here I present the outcomes of both the theories for the dependence of the radius of the inversion ring against the radius of the cavity. And the scenario is qualitatively different within the two theories. We see that the classical theory predicts a linear profile, whose slope is given by Rooster 0. And so it depends only on the elastic anisotropy, and so on the relation between K11 and K22 and K23 and K24. But in the quadratic theory, we predict a nonlinear dependence of R star as a function of R. And an attempt toward understanding of which of the two theories better describe the experimental result I plot with these red boxes the experimental radius of the inversion ring of the cavities I have from the experiments against the corresponding value of the radius of the cavity. And we see that it seems that our star is distributed in the distribution of our star is non-linear as a function of R. And here our star and our from the experiments are normalized to this characteristic length predicted, estimated for the samples observed after 1 day, because all the data belongs to these samples. And indeed, our theory can theoretically predict the dependence of our star on R, both divided on this value of on R, and so it does not depend on the particular value of A. I recall that we have find other two estimates for the value of A, also for the samples which are newly done, and those samples observed after 2 days. And I try to apply all the arguments to these cases, and for the samples newly done, where now the experimental radius and the radius of the cavity observed experimentally are now normalized to the estimate of A we have provided for samples newly done, and also for samples observed after 2 days. And I collect in this slide all the results, and it seems that the quadratic theory captures the non-linear dependence of R star as a function of R. And in particular, it seems to suggest that the classical theory is does not characterize the defect core that chromonically crystals generate when they are confined in spherical cavities. And then to sum up, we studied with twisted hedgehog defects and their core structure that the chromonically generate when they are confined in these spherical cavities with homotropic boundary conditions, and 3 features which are in stark contrast are predicted by both theory. 2 are qualitative and 1 is quantitative. And on the quantitative side, we have that the core defect estimated to be 1 order of magnitude larger than in the classical theory. And on the qualitative side, we have that in the quadruplet theory, the director described Archimedean spirals instead of logarithmic ones, and there is a nonlinear dependence of the inversion ring on the radius of the spherical cavity. And the feature predicted by our theory seems to be well confirmed by the experiments, and so we can say that the defect core could be the hallmark of the quadratic elastic theory for chromonically crystals. Thank you very much for the attention. And
more questions. This is more of a remark. Firstly, I really enjoyed my talk. It was really exciting.
thank you very much.
And I mean, I do have a remark though. The twisted defect structure, you're right. It could be a hallmark of CLC, and you captured it using a reported theory. But this has been observed in experiments, especially during a temperature-dependent transition. And I have some work with Jan Laverbold, who's also an experiment. There is evidence that the boundary conditions actually change as you change the temperature. And you will get the same twisted structure for a hybrid structure. Or something where you basically use the perfect homeotropic angle. So that could also lead to twistedness of your perfectly radial hedgehog profile in this study. And that's one reason. And the next we can just talk about that. We can just have a proper chapter.
Yes,
questions? Well, if not, okay, thank you.
Do these defects like, I mean, I have no idea of the kind of a pretty stupid question.
No, I,
Do they interact with each other? Like, for example, in metal, when you have these defects that kind of move, does something like that happen?
yeah, they can move. It's a real, maybe when we change the temperature, but we need to study dynamical systems, and here I study equilibrium configurations, but there are studies with moving effects, and they can form discriminations and so on, but this is focused on the equilibrium. Thank you.
No, just generally trying to understand it. And so, like, for example, sorry.
No, it's okay, okay, go ahead.
You talked about it, like about the fracture. You just made a sentence in that. So are these defects kind of points where the fracture might initiate or something, or?
Yeah, it is a really good question, and I'm working on fractures, and I'm trying to work in business last month on fractures, and it is a very good question. I don't know, because in this case we have a boundary which is fixed, and so we don't have circulation of the surface inside the droplets, and so it is not observed. But I think that there could be study in which this percolation happens, and I found some work with equilibric liquid crystals where there is a percolation of the surface and the droplet split. But in this case, there is no. But sometimes there are studies, for example, with bend twist material, where there are considered fractures in pneumatic liquid crystal, which are not from the boundary but from the director field, and so they form wall defects or discrimination, and it is a very beautiful area in which I'm trying to to enter. Thank you for the question. Yeah.
Yeah, you added the quantification term in T, yeah, to account for the experimental test. So what if you added the quantification term in S, for instance? It would be useful for some experiments.
Okay, okay. And I want to find a minimalistic quartic theory, because my aim is to have a double twist configuration as a ground state, and so I only need to add one term, because more terms, more higher order terms we introduce in the model, more the model is difficult. And so I only take the property which Chromonic liquid crystals have in 3 dimensions, and then I try to construct the minimalistic triangle that can give me the opportunity to describe these Chromonic liquid crystals, because, for example, I could have introduced also second derivatives, and not only in the gradient of n and so on, but there are a lot of possibility, but they are analytically very, very, very difficult, and so I thank you for the question.
Last question, this parameter A, which at present is a model parameter, but could you work out, say, the objects for a given value of K11, K22, K33, K24? Can A be worked out as part of some sort of optimization problem, or do we minimize the energy with respect to A?
For me, A is a problem, because we don't know from what where we can on what it depends, because we consider it as a fixed, but I think it's fixed by the temperature, the concentration in the solvent, how much polymer is in the concentration. But for my experience, I consider A fixed, and I found it with the study of this direct observation. But I think that a microscopic model is necessary to study this A, because I think it depends on the persistence length of the molecular aggregate, or the fact that the column are large, but they can interact between each other. I don't know what it is. That I consider it fixed for these physical conditions of the material, but a study has to be done from the macroscopic point of view. Thank you.
Okay, and no more questions. Let's.
Thank you very much.